Hi, I'm going to talk about engraving, and particularly engraving into corners, and just explore some of the options and some of the effect of tool geometry and all of that. So let's say I've got these two rectangles that I want to engrave in between. These things are a ½ inch apart, and so if I wanted to engrave down with say a 90-degree conic tool, I want to engrave till I have that ½ inch width there. One of the options would be to create my own offset and offset it. Create my own offset here and offset it to the inside of the outer line, halfway in between, in this case a ½ inch or a ½ inch. And I click apply, and I could just do a simple 2D engrave using a 90-degree conic, and I would go down a ½ inch and tell it that it's just a 2D engrave, not a 3D engrave, and click apply, and you see that the toolpath gets created on top of the contour. And if I look at it in the perspective view, it's just a flat contour down that ½ inch. So if I simulate, I'll come back up here and I'm going to simulate just the corner. And so I click on 3D simulate and click OK, and so now I'm going to simulate what that looks like. Remember, this is a 2D engrave, and it does a nice job. You can see that I get the ½ inch width, and it goes around the corner correctly and everything. The downside, or the potential downside, of this type of engraving is that on the outside of that corner it's rounded, because the tool is rounded, and as it makes that turn it's going to have a rounded corner. So you might have the desire to have a sharp corner there, sharp inside corner we call that, and in order to accomplish that I need to do a 3D engrave. And so in order to do a 3D engrave, what I'm going to do is, I'll move this out of the way so it's not confusing. What I'm going to do is I'm going to select this rectangle, and I'm going to select the one inside, so it's the ½ inch offset, and I'm going to do a 3D engrave in between those two squares. So if I select this and I want to go 3D engrave, the difference is I want to allow the tool to go a little bit deeper, and we'll see why here in just a second. But basically I'm going to go that ½ inch width, and what EnRoute does is it calculates, based on the tool geometry, it calculates the depth that it wants to go. But you notice that the geometry changes in the corner here a little bit, where it pulls away from the corner. It essentially splits the difference between the geometry, and as the geometry gets further apart it has to change that offset. And where you really see it is in the vertical plane. So you see that geometry also goes down in order to use the width of the tool to engrave these straight outside edges and inside edges here. So the geometry is going down in order to maintain those straight edges. So let's do a simulation of that. But what I'm going to do is I'm going to take that first geometry that we engraved, that 2D engrave, and I'm going to move it inside so that we can sort of compare what they look like. Now, use that rectangle for simulation and click OK, and let's simulate them and see what they look like. Okay, so now you see that the 3D engrave does some different things. It maintains that straight outside edge all the way into the corner, and then it goes up and creates that beveled inside corner, which the 2D engrave does not do. And so it is more true to that square corner on both the inside and the outside, and the way it accomplishes that is with this geometry and then going up into the inside corner. Now there's one sort of catch to this, and it is that the the geometry of the toolpath that was created is dependent on the tool being defined precisely as the actual tool is that we're going to be using to cut. And so if the actual tool geometry is different, and sometimes even a little bit different, what can happen is the results that I get for these edges will not be perfectly straight because the actual geometry of the tool is different than what was calculated for this toolpath. And this toolpath is not just a straight 2D toolpath. It drops down in the z-axis and then it goes up into the corner. So it depends on that geometry being precise. So let's look and see what might happen if the actual tool geometry is different than what I assumed. So if I go to the 90-degree conic, and let's say that angle changes by just let's say 5 degrees. So instead of being a 90-degree total angle, it's an 80-degree, or 2 times that 40. So it's an 80-degree angle. Now that's probably more different than what it might actually be, but even a couple of degrees can make quite a noticeable difference. So if I change this, so now I'm going to simulate this again with the changed tool geometry, and I haven't told the toolpath that changed, so it's calculated based on that 90-degree conic. So let's go back here and see what that looks like. Okay, so you can see that the 2D toolpath looks pretty much like it did the first time, because all that happened is the tool geometry changed, and so that angle changed. But since it was just 2D toolpath, it didn't really noticeably affect the difference. If you measured the width of this, you would see that the width of this was narrower than the half-inch width that you assumed. But with the 3D toolpath, you can see that instead of maintaining that straight edge, particularly on the outside, you can see that what happens is it sort of tapers in a little bit. And you can also see on the inside corner a little bit less noticeably, but you can see that it's rounded instead of coming to a point. And so if you see in a cut this type of result, probably what happened is your tool has a little bit smaller angle than you have defined, and so you really need to calibrate the tool in order to make sure that what you're calculating in the toolpath is representative of what you actually have. So now let's go back, and we'll go back here, and we're going to change the tool geometry again, and instead of 40 degrees, let's go 50 degrees. So in other words, it's a bigger angle. The tool is flatter than it was assumed in the toolpath. And let's do that simulation again. Okay, so now you can see what's different here is that instead of necking down as I approach the corner, it gets fatter as I approach the corner, meaning that the tool, since it's flatter, as this geometry changes, instead of maintaining that straight edge, it bows out because of that flatter tool. And here you can see that the sharp corner kind of goes down in a little bit. So that's what the result of the difference in the toolpath relative to the actual tool, what effect it has on the finished cut. And so this is another symptom that you might see with a cut where it looks like it didn't square off the corners, and what it's telling me is that the tool geometry is actually different than what was assumed in the tool definition. And this can happen with the angles being different. It can also happen if the tool, the conic tool, doesn't come to an actual point and has a flat surface on the tip that's not accounted for in the toolpath. That can also have that effect on changing the results here. And so it's really important that, particularly with the 3D toolpath, that the tool geometry as defined in EnRoute matches the actual tool geometry that you're using when you cut. Otherwise, you're liable to see corners that look a little raggedy like this and are not what you're going for. So now if I change the tool back to 45 degrees, which is as it was calculated, and I do a simulation, like we did the first time, you can see that I'm back to having that straight edge, and this is what you get if your actual tool geometry in your machine matches the tool as defined. So sometimes what it takes is doing some sample cuts in order to calibrate the tool. It's a little bit hard to measure that angle, but you can adjust the angle and do some calibration cuts in order to determine the actual geometry of the tool when you get results that are exactly as defined or as you would expect to get based on the toolpath. So that's the 2D engrave versus 3D engrave, and really the importance of the tool geometry matching the geometry of the tool that you're using in the machine, and what you might see in situations where the actual tool geometry doesn't fully match the way you defined it. So I hope this helps, and thank you.